how it is affecting the reaction of these compounds. Now let us briefly tell you what is aromaticity. Aromaticity. Now, suppose you have a compound like this. You have one double bond. Okay, you have a double bond. Now, if you look at the energy of this molecule and compare with that of this molecule, okay, okay, good, good. I'll write 7, good. Now, if you compare the molecule, this molecule with this molecule, you have a double bond. And see if the energy of this molecule of a single bonded compound is lower than the energy of a double bonded compound. So you have, if this is the level of the single bonded compound, the energy of this molecule, then this will be the energy of this molecule. Okay. Now, if you have, I will just make it a cyclic ring. That is better. I will make it a cyclic ring because we are going to deal with cyclic compounds. So I'll draw a 6-membered ring. I'll draw a 6-membered ring. See here. Cyclohexane, simplest molecule. This is the energy level. Cyclohexene has got one double bond. This is the energy level. And now cyclohexadiene. You have to. So one double bond contributes this much of energy. That means when you have introduced one double bond, the energy of the molecule increases by this factor. That means it becomes more unstable, more reactive. That's what you have to remove. So correspondingly, if you add one more double bond, approximately this much of energy is added. So in fact, if you add one more double bond, you expect the energy to come to this level. If you add one more double bond, suppose you add this much of energy here, you expect the molecule to have this much of energy. Okay, so this is the expected energy level. On a cumulative basis, when you add one after the other, okay, assuming that each double bond contributes a definite amount of energy, then you expect this to be the energy level of benzene. But in reality, this is expected. See, the actual energy of benzene is somewhere here. Meaning, it is having this much less energy than expected. This energy is known as resonance energy. Resonance energy is the stabilization factor. It's a stabilization factor of aromatic compounds. Okay, that means when you have 3 double bonds in a cyclic ring, conjugated double bonds, 3 conjugated double bonds in a 6-membered ring, The molecule is expected to be more stable. Molecule expected to be, found to be more stable than expected. They're found to be more stable than expected. That difference. Now, more stable means lowering of energy. Lower energy. Lowering of energy. And how does it affect? How does it affect the reactivity of the molecule? The reactivity is affected. What way? See here. If we have a one double bonded compound and react this with bromine, you will get a dibromo product. See this. What is the type of reaction here? Addition reaction. If you have a molecule like this can give you, if you had only one molecule of bromine, you will get this product or you will get this product. 1,4-dibromo or 1,2-dibromo compound. So again, this is an addition reaction. This is an addition reaction. But if you take a molecule with three conjugated double bonds in a cyclic ring and do a bromination reaction in presence of a FeBr3, we have studied this. Okay, we have studied this. What is the product of this reaction? The product is Br, a substitution product. So aromatic compounds undergo substitution reaction than addition reaction. Okay, than addition reaction. So this is the consequence. Addition is not very easy. Addition is not very easy in the case of aromatic compounds. They undergo substitution reaction. Okay, and this is, so that means breaking this double bond is not very easy, and that is why you can replace this hydrogen, but you cannot add. You will find it difficult to add to bromine. Of course, there are reactions in which you can add halogens, but conditions are different. Okay, so this is a consequence of aromaticity. Now let us see what is meant by aromaticity. Now, what is aromaticity? Aromatic character. What is aromatic character? There are 4 conditions to be aromatic. 4 conditions for a compound to be aromatic. Compound to be aromatic. What are the four compounds? Number one, there should be, it should be a cyclic compound. You know what is a cyclic compound? Closed rings. Okay? So it should have a cyclic compound with conjugated double bonds. Right? Cyclic, that's the first condition. Second condition, it should be planar compound. The molecule should be planar. I have already shown you the structure of the ring, benzene ring. See this? You remember this? The figure which we have drawn. This is the benzene ring. And see all the carbon in a single plane. You have the hydrogen here, H here, H here, H here, H here, and H here. See everything in a single plane. And then you have a cloud on the top and bottom. See here. So it is a planar ring. All the carbons are sp2 hybridized. sp2. Trigonal planar. See. See this. This is to the front, and this is towards the back side. This back side I have not drawn like that, but it is, you know, it is. This is on the back side. This is projecting back. Okay, so this is so it should be planar. So this is the second condition for a compound to be aromatic. It should be planar. Number three, it should contain a p orbital. It should contain. It should have a p orbital on each atom of the ring. Okay. It should have a p orbital on each atom of the ring. So that is the next condition. You can see here. Here is a p orbital. Here is a p orbital. It's a p orbital. Here is one. Here is one. Here is one. Okay, the p orbital may or may not contain electron. All the p orbitals may or may not contain electron. At least some of them definitely will have. Okay, so that is the third condition. And fourth condition is known as Huckel's rule. It should contain, should have a total of 4n plus 2 pi electron. 4n plus 2 pi electron. This fourth condition is known as Huckel's rule. Huckel. Huckel's rule. Okay. So this is these are the conditions for aromaticity. So planar, cyclic, containing p orbital, and 4n plus 2 pi electron. Such molecules are aromatic molecules. Okay. Now what about this one? And what is this n? N is an integer. N is an integer starting from 0, of course. 0 is an integer, right? normally positive integer. Okay, now let us see whether we can apply this rule for benzene molecule. Let us see whether benzene is aromatic under this condition. Now benzene is cyclic. It is cyclic. It is planar. Planar. And it is having 6 p orbitals. It is having 6 p orbitals. And what about the 4n plus 2 ring? Now look, how many pi electrons are there? See, 3 double bonds, 6 pi electrons. 6 electrons. So 6 electrons should be equal to 4n plus 2. This is how you have to calculate. Therefore, 4n equals 6 minus 2 equal to 4. Therefore, n equals 4 upon 4 equal to 1, a positive integer. So the molecule is aromatic. Is it clear? Okay, let us look at this molecule. Why don't we look at this molecule? Yeah, again, you can see it's alternate single and double bond. It is cyclic. It will because see whenever there is a double bond, there will be a p orbital. Here is a you have a p orbital. Here you have a p orbital. Here, and here, and here. Everywhere there is a double bond. That means there is a p orbital. Now let us apply the 4n plus 2 rule. See whether it is working. 4n plus 2. How many? Count the number of electrons inside. 2, 4, 6, 8, 10. There are 10 pi electrons in the system. So 4n equals 10 minus 2 equals 8. N equals 8 upon 4 equals 2, an integer. Clear? Suppose you look at this molecule. Let me take its cyclo. What is this molecule? What is this molecule? It's a diene, 4 carbons. So it is cyclobutadiene. Cyclobutadiene. Is it aromatic? Let us see that. Is it planar? Yes. You have sp2 carbon, sp2 carbon, sp2 carbon, sp2 carbon. So it should be planar. There should not be any doubt about it. Is it cyclic? Yes, it is cyclic. It is having, since it is sp2, there should be a p orbital on each of these unhybridized p orbital should be there. Because it's cyclic and it's having H planar, sp2. So there is unhybridized p orbital. But what about 4 plus 2? How many electrons are there? 2 plus 2 equal to 4. There are 4 electrons. So we will equate 4n plus 2 equal to 4. N plus, 4n equal to 4 minus 2 equals 2. N equals 2 upon 4. Am I right? Equals 1 by 2. Not an integer. It is not an integer. Okay. So this molecule, it exists but highly unstable, not stabilized. Now, which rule this compound apply? For this compound, suppose you put 4n equal to 4. Now it will be an integer. Okay, 4n equal to 4. Now that will be an integer. Let me write it. Okay, now, so 4n is equal to 4, therefore n equal to 1. Such compounds, which follow all these conditions except 4n plus 1, you have 4n rule. Such compounds are called anti-aromatic compound. Anti-aromatic compound. So you have anti-aromatic compound and aromatic compound. What's the difference in the rule? All other conditions same. Cyclic, planar, and containing p orbital, on each atom. Containing p orbital on each atom. And obeying 4n rule, number of pi electrons. Contain 4n pi electrons. Such compounds are known as anti-aromatic compounds. So you have anti-aromatic compounds and aromatic compounds. And remember, you have non-aromatic compounds also. Okay? Non-aromatic compounds does not obey any of these rules. Clear? So these are the types of compounds which we come across in this. Now let us look at some other aromatic species. Look at this one. See here. Cyclopropene. It's not cyclopropene. Cyclopropenyl cation. This is known as cyclopropenyl cation. Cyclopropenyl cation. Okay. Now cyclopropenyl cation. See this. It's a cation, that means it's in the positive charge. So let me draw the structure. Let me draw the planar ring. See, here is a double bond. That means you have a p orbital here, and an empty p orbital here. There is one electron here, and they will interact. They will form a pi bond. See here. This will form a pi bond. What about this one? This is empty. That is empty. Okay. So this molecule, it is planar. It is planar. All the carbons are sp2 hybridized. What about this carbon? Look at this carbon. You have one hydrogen here, positive charge, one hydrogen here, one hydrogen here. Okay. So this carbon is, what is the shape of this carbon? The shape is hydrogen. And you have an empty p orbital perpendicular. So this is the shape, right? So this molecule is cyclic, it is planar, cyclic. You have p orbital in each p orbital, and how many electrons it contains? It contains 2 electrons. See here, 1 double bond, 2 electron. 2 equals 4n plus 2. Therefore, for n equals 0, n equals 0, an integer. So it is aromatic. It is aromatic. Then you have cyclopentadienyl anion. Cyclopentadienyl anion. Now cyclopentadienyl. So you have to draw a cyclopentane ring. So this is a cyclopentane ring. Let me draw a cyclopentane ring in this fashion. See, 5 carbons. 5 carbons. Okay. Now you have a pair of electrons here. That's why we say it is anion. This orbital is containing an anion. Now you have a double bond here and here. Let me draw the planar structure first. This is the planar structure. Dienyl. 2 double bonds. That means you have a p orbital here, 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 and here. And remember, each one of them is contributing 1 electron. Each p orbital contributes 1 electron. And this orbital only contributes 2 electrons. Now what is the total number of electrons? 6. So 4n plus 2 equal to 6. And n equals 1. So this is a example for a anion which is aromatic. Similarly, you have another cation which is aromatic, cycloheptatrienal cation. So this is 3-member ring, this is 5-member ring. Let us look at a 7-member ring. Look at a 7-member ring. Yes. And this is a cation. Plus. Again, you have the same situation. Okay, total 6 pi electrons. 6 equals 4n plus 2. Therefore, n equal to 1. So all these compounds are aromatic. Now, similarly, you have certain other compounds which are neutral molecules, which normally you will think it is not aromatic. See this one. Normally we will think this is not aromatic. Because the nitrogen lone pair is not actually, you will think that it is not contributing any. It is a sp2 hybridized, sp3 hybridized. But actually, when this molecule forms, what really happens is this nitrogen becomes sp2 hybridized, and it exists in a planar fashion. See here. And this orbital, in which there is lone pair, it changes its direction slightly and be aligned with these orbitals here. So even though there is no double bond on this nitrogen, the lone pair will contribute that electron into this cloud. And therefore, this molecule is aromatic. Similarly, you have all these, they also are aromatic. There are two lone pairs here. One lone pair will be like pi bond, other lone pair will be just projecting out like a sigma bond. So this is aromatic. Okay, similarly you have this compound, sulfur. There is a lone pair of electron. There is a lone pair of electron, and that also is aromatic. This is called thiophene. Thiophene. And this one is pyrrole. Okay. Then pyrrole, thiophene. This is not pyrrole. See, sorry. This is furan. Furan. And this is pyrrole. And then look at these two compounds. I have two compounds here. Same, very similar. This is called quinoline. You have a lone pair of electrons here. This is very confusing. See here, quinoline and pyridine. If you have a double bond already, the lone pair will not be part of this ring. Compare this and this. Compare these two. See here. Here there is no double bond between this. So this lone pair is part of the ring and become aromatic. Here there is a double bond between the nitrogen and the carbon, and therefore this is not part of the aromatic ring. Okay, so what is the geometry of this molecule? Look here. Look at the geometry. Here is nitrogen, and lone pair is just like these hydrogens. See this. See. And you have now yeah. And here also there is an empty p orbital. There is an empty p orbital. And this will contribute one electron. See this. And therefore, this electron is part of the ring. This electron is not part of the ring. Not part of the ring. So when you have one electron, one double bond already, then lone pair will not be part of the ring. But if you don't have a double bond, then the lone pair will be part of the ring. Okay, provided all other conditions are satisfied. That is what you have to remember. All other conditions should be satisfied. So these are the aromatic. Okay, and these are known as non-benzenoid compounds. Non-benzenoid.